On April 13th, 2029, something will pass through the zone of space where humanity has placed its most critical infrastructure. Not outside it, not near it, through it. Below the ring of satellites that carry your phone calls, your weather data, your GPS coordinates, your financial transactions, your emergency broadcasts, the quiet, invisible architecture that modern civilization depends on without thinking about it for a single second of any given day. A space rock the size of the Empire State Building will thread the needle between the surface of the Earth and the machines we have built to extend ourselves into orbit. That number, 32,000 kilometers from the surface of our planet, deserves a moment of real stillness before anything else is said. Geostationary satellites, the ones that form the backbone of global communication and weather monitoring and navigation, hover at 35,786 kilometers above the surface. The asteroid Apophis will pass closer than that. It will pass below them. In the 4.6 billion year history of this solar system, no known object of its size has ever entered that zone during any period when human beings were present on the surface watching. We have never, in the full stretch of recorded astronomical history, had the instruments to witness what is coming in 2029. 8%. That is how much of the asteroid tracking community had heard of the 1 in 37 impact probability that briefly appeared in the calculation tables of 2004. Most people have never encountered that number. Most people have never heard the word Apophis in any context other than a passing news alert they scrolled past and forgot. But if you were working in near-Earth object research in the winter of 2004, if you were one of the people whose job it was to assess the orbital trajectories of newly discovered asteroids and determine which ones needed to be watched more carefully, you encountered a probability that no one in the history of the discipline had ever seen attached to an object of this size. And then you had to decide what to do with it. Stay with me, because what this asteroid is, what it did to the people who found it, what it will do when it arrives, what it is already doing to the way we think about the neighborhood of space we inhabit, and what it will leave behind when it passes through that satellite zone and continues on its way, is considerably more interesting than a close call. This is not a story about something that was supposed to hurt us, and will not. This is a story about something that is about to show us, for the first time, exactly where we live. Apophis, the god of chaos, named after the ancient Egyptian serpent of eternal darkness, the enemy of Ra, the being who every night sought to swallow the sun and plunge the world into a darkness from which it would never recover. Discovered in 2004, tracked for 20 years, arriving in 2029 on a Friday the 13th, passing through the space between our satellites and our planet at 26,500 miles per hour, visible to the naked eye of approximately 2 billion human beings who will look up at a sky they have looked at every night of their lives and see for the first time an asteroid. The astronomers are not panicking. But that is not the same thing as saying they are calm. What they are is something more interesting than either of those words, and by the time we reach the end of this, you will understand exactly what I mean. Let us begin. There is a reason the people who discovered this asteroid named it after the Egyptian god of destruction, and the reason is not poetic license. It is that for a brief but measurable period of time in 2004, the data they were looking at was genuinely frightening. On the evening of June 19th, 2004, 3 astronomers working at the Kitt Peak National Observatory in Tucson, Arizona, found something they were not expecting. Roy Tucker, David Tholen, and Fabrizio Bernardi were running a systematic sky survey. The object they flagged in their data was unremarkable at first glance. A small point of light, moving the way near-Earth asteroids move across a series of exposures, caught by the sweep of the telescope in the ordinary course of a night's work. They recorded it. They logged it. They flagged it for follow-up observation and moved on. What the data they had collected actually contained was not apparent until the calculations came back. The object had an orbit that brought it toward Earth in a way that caught the attention of every person who saw the numbers. Within weeks of its discovery, enough observations had accumulated that orbital mathematicians at the Center for Near-Earth Object Studies, the group at NASA's Jet Propulsion Laboratory, whose specific job is to assess the impact risk of newly discovered objects, ran the trajectory through their models. What they found was that the asteroid had a calculated probability of impacting Earth in 2029. Not a theoretical possibility. A calculated probability, based on the best available measurements, that this specific object was on a path that could end at the surface of our planet. That probability rose as more observations refined the calculation. By December 2004, it had reached 2.7%. At certain points in the refined analysis, given the uncertainty bands in the early orbital solution, some calculations placed the odds as high as 1 in 37. To understand what that number meant in context, consider the broader landscape of what planetary defense scientists track and assess. The Century Impact Risk Table maintained by NASA's Center for Near-Earth Object Studies is a catalogue of every asteroid whose orbit comes close enough to Earth that an impact in the foreseeable future cannot be mathematically ruled out. Most entries on that list have probabilities in the range of 1 in several million, or 1 in tens of millions. The presence of an object on the table means the orbit is not yet well enough constrained to eliminate the possibility of a collision, not that the collision is likely. The typical entry on the risk table represents a statistical whisper, a level of concern that requires continued tracking but no immediate alarm. An asteroid with a 2.7% chance of striking Earth in 25 years was something the table had never seen. It was not a statistical whisper. It was the loudest signal the planetary defense community had ever received from the sky, attached to an object large enough that the consequences of an impact would have been catastrophic for whatever region it struck. The media response was immediate. The words asteroid and impact and Earth and 2029 appeared together in coverage that ran in newspapers and on websites in dozens of languages. The language of apocalypse was invoked freely because the circumstances invited it. A rock in space had been found on a trajectory toward our planet. The probability that it would arrive was not zero. It was, for a window of weeks, higher than any probability ever previously associated with an object of its size. The International Astronomical Union approved the name Apophis in 2005. In Egyptian mythology, Apophis, sometimes rendered as Apep, was the serpent of chaos and darkness, the eternal enemy of order and light. Every night, according to the mythology, Apophis rose to consume the sun as it passed through the underworld on its nightly journey, and every night Ra and his allies fought the serpent back so that morning could come. Apophis was never defeated permanently. The battle was eternal. The darkness was always waiting. The discoverers of the asteroid chose the name deliberately, because the possibility they were looking at in their data was exactly that kind of threat. Not certain, not defeated, waiting. Additional observations change the picture, as they almost always do when an asteroid is newly discovered, and the orbital solution is still rough at the edges. When there are few measurements over a short arc of observation, the uncertainty in the orbital solution is large. Possible trajectories fan out across a wide swathe of space around Earth. As more observations come in, the fan collapses. Positions that were possible become improbable, and then impossible. The range of trajectories consistent with all the data narrows, and as the range narrows, the question of whether Earth lies inside it or outside it becomes answerable. By 2006, the 2029 impact had been ruled out. The fan of possible trajectories had collapsed enough that Earth was no longer inside it. The orbital solution had improved to the point where the closest approach distance was known well enough to determine that Apophis would pass near Earth, dramatically near Earth by any historical standard, but would not strike it. By 2013, additional radar observations from the Goldstone Deep Space Communications Complex in California and the Arecibo Observatory in Puerto Rico had ruled out the possibility of a 2036 impact. An impact in 2036 had been the second concern after 2029 was eliminated, a follow-on scenario driven by the physics of gravitational interaction that we will examine in detail in a later section. And in March 2021, after radar observations conducted jointly by the Goldstone Complex and the Green Bank Observatory in West Virginia pushed the orbital uncertainty down to a handful of kilometers rather than hundreds, David Farnocchia of NASA's Center for Near-Earth Object Studies announced that a 2068 impact was no longer in the realm of possibility, and that the model showed no impact risk for at least the next 100 years. Apophis was formally removed from the Century Impact Risk Table on February 21, 2021. The table that had never contained an object like it lost its most famous entry. The asteroid that had briefly held a 2.7% chance of ending a city was reclassified from a hazard under assessment to a scientific opportunity of the highest order. But here is the thing that the announcement of safety does not fully capture, and the thing that gets lost in coverage that treats the Apophis story as a threat averted. The removal from the risk table did not mean the story was over. It meant the story changed. An asteroid that was terrifying because it might arrive is, it turns out, an equally extraordinary object because of what its actual arrival reveals about the system we are part of. What kind of story does an asteroid tell when it stops being a threat and starts being something else entirely? The answer to that question is what the rest of this is about. The god of chaos was discovered 20 years ago in a sky survey that was looking for exactly this kind of object. The discovery system worked, the assessment system worked, the orbital refinement worked, and now, as the arrival date approaches, the scientific apparatus built to study close approaches of significant near-Earth objects is preparing for the most important natural experiment in the history of planetary science. Apophis is coming, and we are ready for it in a way we have never been ready for anything that crossed the boundary of the space we thought was empty. The question of what we will learn from it is the question that keeps the astronomers awake. Not worried. Awake. There is a difference. Worry is passive. This particular kind of wakefulness is the feeling of standing at the edge of something genuinely new, with the instruments to understand it, and knowing that the window only opens once. Every few thousand years, on average, an asteroid of this size passes Earth as closely as Apophis will in 2029. In every previous passage, there were no telescopes, there was no radar, there was no orbital mechanics, there were no spacecraft waiting to follow the asteroid through the encounter. There were only people on the surface of the planet, looking up at a sky that contained something they could not name, moving in a way that nothing else moved, and then gone. This time, we know it is coming. We know exactly how close it will pass. We know what it is made of, roughly. We know what it will do to the space between it and us as it goes by. We know how many people will be able to see it. We know what colour it will appear in the sky, and how fast it will move and at what angle relative to the horizon it will cross from east to west. And we are sending machines to ride alongside it, so that for the first time in the 4.6 billion year history of the solar system, the universe's experiment on an asteroid gets watched by the species whose planet it is running the experiment near. That is the story of Apophis, not what it was going to do to us, what it is about to show us. Those are very different stories, and only one of them is worth the attention this is going to receive in 2029. The other story, the threat story, ended in 2021. That one is finished. This one is just beginning. The number 32,000 kilometers requires translation before it becomes something your nervous system can actually process. Because the way we encounter large numbers is almost always mediated by comparison, and the comparisons that are usually offered in coverage of asteroid close approaches tend to flatten the magnitude of what is actually being described rather than illuminate it. 32, 0 kilometers. That is the approximate distance at which Apophis will pass the surface of Earth at its closest point. To give that number something to push against, consider the following. The Moon orbits Earth at an average distance of 384,000 kilometers. Apophis will pass at roughly 1/12 of the distance to the Moon. The Moon is the nearest large body in space, the most visible object in the night sky after the Sun, the destination of the first humans to leave their planet. The Moon, by the standards of interplanetary distances, is practically in our backyard, and Apophis will pass at 1/12 of even that distance. The International Space Station orbits at approximately 400 kilometers above the surface. That is roughly 80 times closer to Earth than Apophis will come. The ISS is close enough that on a clear night you can see it without a telescope moving steadily across the sky. It is close enough that its crews can see individual storms and mountain ranges below them. 400 kilometers is what close looks like from a human operational standpoint. Geostationary satellites, the ones that handle television broadcasting, GPS navigation, weather imaging, and the global communications infrastructure that the modern world runs on, orbit at 35,786 kilometers above the surface. That altitude is chosen specifically because at that height, the orbital period of a satellite exactly matches the rotation period of Earth, 24 hours, meaning the satellite appears to hover stationary above a fixed point on the ground. Every satellite television dish in the world points at a fixed spot in the sky because the satellite it is talking to is stationary at 35,786 kilometers. Apophis will pass at 32,000 kilometers, which means Apophis will pass inside the geostationary ring, below it, between the geostationary satellites and the surface of the planet. In the zone of space that humanity has designated as one of its most critical operational domains, where machines we depend on every day hold their fixed positions in a ring around the Earth, an asteroid the size of a skyscraper will move through at 26,500 miles per hour. There is no credible collision risk to the satellites. The trajectory of Apophis is inclined away from the equatorial plane, where geostationary satellites are concentrated, and the asteroid's path does not carry it through any densely populated orbital region. The fact of the passage is not a physical danger to the infrastructure, but the geometry is something that has never occurred in the entire history of human civilization and satellite operations, and that fact is worth sitting with. We built those satellites. We placed them in those orbits with extraordinary care, in a region of space we consider close to Earth by any spaceflight standard. We depend on them for things that feel invisible and routine until they stop working. And something the size of the Empire State Building is going to cross through that region on a Tuesday evening in April 2029 and keep going. The speed at closest approach is worth considering as well. At the moment Apophis reaches its closest point to Earth, 21:46 Universal Time on April 13th, 2029, it will be travelling at approximately 7.4 kilometers per second relative to Earth. That is a number generated by Earth's gravitational field pulling the asteroid inward and accelerating it as it passes. Before the encounter, Apophis will be moving at roughly 6 kilometers per second relative to our planet. As it falls toward closest approach, Earth's gravity accelerates it to 7.4 kilometers per second. As it departs, the same gravity slows it back down to approximately 6. The asteroid experiences a gravitational acceleration and then a deceleration, and the net effect of that interaction is a permanent change to its orbit. But at the moment of closest approach, at 7.4 kilometers per second, Apophis is moving at approximately 26,500 miles per hour. Consider what 26,500 miles per hour means for the satellite zone it will pass through. A bullet fired from a rifle travels at roughly 2,000 to 3,000 feet per second, or approximately 1,500 to 2,000 miles per hour. Apophis will be moving 17 times faster than a rifle bullet as it crosses through the space where our geostationary infrastructure lives. The brightness of the asteroid at closest approach will be approximately magnitude 3.1. The astronomical magnitude scale is counterintuitive, with lower numbers representing brighter objects. The brightest star in the night sky, Sirius, sits at magnitude negative 1.46. Most stars visible to the naked eye from a dark location fall between magnitude 1 and magnitude 6, with magnitude 6 being roughly at the limit of unaided human vision. Apophis at magnitude 3.1 will be easily visible to the naked eye from any dark location, comparable in brightness to a moderately bright star in a familiar constellation. But Apophis will not look like a star, not to anyone paying close attention. Stars do not move. On the timescale of a few minutes of observation, a sufficiently attentive observer will be able to watch Apophis shift against the background of fixed stars, a point of light sliding across the sky at a rate that makes its motion apparent without any instrument. Over the course of the full observable window, the asteroid will trace an arc of approximately 205 degrees across the sky, moving from the constellation Centaurus in the southwest, through Perseus in the north, and down into Pisces in the southeast. It will be visible from Europe, Africa, and Western Asia. Approximately 2 billion human beings will be in regions where the asteroid is observable, given clear skies. 2 billion people. The population of Europe is approximately 750 million. The population of Africa is approximately 1.4 billion. The population of Western Asia adds hundreds of millions more. There is no astronomical event that has been simultaneously visible to this many people from such a wide geographic range in the documented history of human civilization. Not a meteor shower, not a comet, not a lunar eclipse. The number of witnesses to the 2029 Apophis flyby, measured as a fraction of the total human population, has no historical precedent. And virtually every one of those 2 billion people will be watching something they have never seen before and may never see again. An asteroid in the sky above their house, moving. The timing is precise enough to state almost to the minute. On April 13th, 2029, at 21:46 Universal Time, Apophis will reach its closest approach to Earth. That is 9:46 in the evening Greenwich Mean Time, which means the prime viewing window falls in the evening hours for European and African observers when the sky is dark and the asteroid is bright. The conditions for observation are, by some measurement of cosmic irony or coincidence, nearly optimal for the population that will be able to see it. The date itself, April 13th, 2029, falls on a Friday, Friday the 13th, the date most deeply associated in Western cultural tradition with misfortune and danger. The ancient Egyptian god of chaos, named for the serpent of eternal darkness, arriving on the Western world's most superstition-laden date, threading the needle between our satellites and our planet at an altitude lower than our communications infrastructure. The orbital mechanics that produced this calendar coincidence have no awareness of human symbolism. The trajectory of Apophis was determined by gravitational interactions across billions of years of solar system history, by the accumulated effect of Jupiter's gravity nudging its orbit decade by decade, by the thermal push of sunlight on its rotating surface across centuries. None of that physics knew it was setting up a Friday the 13th arrival, and yet here it is, April 13th, 2029, a Friday, an asteroid below the satellites, 2 billion witnesses. The universe does not arrange these things for our benefit or our discomfort. It does not arrange them at all. They simply are what they are, the product of physics playing out across scales of time and space that human intuition was not built to grasp. But when the product of all that physics lands on a date that every culture in the Western world associates with bad luck, on a trajectory that threads the needle of the infrastructure zone of a species that put machines there to keep civilization running, and arrives carrying the name of the god of chaos in a mythology that predates that infrastructure by 4,000 years, the result is a resonance that is worth noticing even if it means nothing at all. What will those 2 billion people feel when they look up and see it moving? That is not an astronomical question, but it may turn out to be the most important question of everything that follows. Most of the conversation about Apophis centers on the 2029 flyby itself. The proximity, the brightness, the satellite zone, the 2 billion witnesses. These are the parts of the story that translate into language that the general public can engage with, and they are real and meaningful and worth understanding. But the flyby is not the most important event in the Apophis story. The most important event is what happens to Apophis because of the flyby, and why the answer to that question required 17 years of calculation, uncertainty, and professional unease before it was finally settled. To understand this, you have to understand a concept that has a name so apt it sounds like it was invented for a science fiction novel, but was actually coined by a real scientist in a real paper in 1999, before Apophis was discovered, before anyone knew this specific object existed. The concept is called a gravitational keyhole, and the man who named it was Paul Chodas, a researcher at NASA's Jet Propulsion Laboratory who has spent decades computing the orbits of near-Earth objects. A gravitational keyhole is a region of space, sometimes only a few hundred meters wide, through which an asteroid must pass during a close planetary approach in order to be deflected onto a trajectory that will lead to a future impact. The word keyhole captures something precise about the physics. The asteroid does not need to hit the planet during the first pass to set up a future collision. It simply needs to pass through a specific, geometrically defined, extraordinarily small region of space during the flyby, and the planet's own gravity will do the rest, bending the path by exactly the right amount to bring the asteroid back around on a collision course in a later orbit. Think carefully about what this means. Earth's gravity, which protects us from many things by pulling meteors and debris into shallow trajectories that burn up in the atmosphere, can under the right geometry function as a precision aiming mechanism. An asteroid that misses Earth by a comfortable margin during one orbit can, if it passes through a keyhole, be redirected by that miss so that it will strike Earth on the next pass. The planet's protective gravity becomes, in the wrong geometry, the instrument of the planet's destruction. The keyhole framework emerged from orbital mechanics calculations long before Apophis existed as a known object. It was a mathematical consequence of the physics of close approaches, a recognition that the range of trajectories a near-Earth object might follow includes not just safe passes and direct impacts, but also a category in between, passes that are safe the first time but are converted into impacts by gravitational interaction. The word keyhole describes the narrowness of this intermediate zone. For any given future impact date, the keyhole is a geometrically small region in the space around Earth, measured not in thousands of kilometers, but sometimes in hundreds of meters, sometimes less. an asteroid travelling through a region of space millions of kilometres across, approaching from a distance of millions of kilometres further away, has to pass through a target area that might be, at the scale of the encounter, functionally the width of a city block. When Apophis was discovered in 2004 and its orbital solution began to be refined, it became apparent that the 2029 flyby was close enough and the orbital uncertainty was large enough that several keyholes associated with future impact scenarios fell inside the uncertainty band of where the asteroid might pass. The 2036 keyhole was approximately 600 metres wide. There was also a keyhole associated with a possible 2051 approach that could have led to an impact in 2068. The question the orbital mechanics team was trying to answer was not just where Apophis would pass in 2029, it was whether it would pass through a keyhole, and if so, which one. This is why the 2029 flyby generated 17 years of intense tracking concern even after the 2029 impact was ruled out in 2006. Ruling out a direct 2029 impact was one step. Ruling out the possibility that the 2029 pass would thread a keyhole and set up a future impact was a much harder problem, because the keyhole is small and the orbital uncertainty was initially large. The two things, the asteroid's probable position during the 2029 flyby and the location of the relevant keyholes, had to be brought into precise enough alignment with each other to confirm that the asteroid would pass outside all of them. The uncertainty band for Apophis's 2029 position in the early years after discovery was hundreds of kilometres wide. The keyholes were hundreds of metres wide. You could not, with early orbital data, determine whether a 300-kilometre wide uncertainty band contained or missed a 600-metre target. The measurement had to be improved by a factor of thousands before the question could be answered. That improvement took years. Each additional observation of Apophis, optical measurements from ground-based telescopes and radar, ranging from the large antenna arrays at Goldstone and Arecibo, shrank the uncertainty. The hundreds of kilometres became tens of kilometres. The tens of kilometres became single digits. The 2036 keyhole was eliminated first. By 2006, the orbital solution had improved enough to confirm that the 2029 pass would fall outside the 600-metre keyhole that would have redirected Apophis toward a 2036 collision. But there remained a smaller keyhole, associated with the 2068 impact scenario, with a probability that stayed above zero for more than a decade. The 2068 keyhole was approximately 2 metres wide in certain parameterizations. 2 metres against a trajectory uncertainty that had to be reduced from hundreds of kilometres. The target was extraordinarily small. The measurement challenge was correspondingly extreme. In March 2021, the Goldstone Deep Space Communications Complex and the Green Bank Observatory conducted a coordinated radar observation campaign on Apophis as it made a moderately close pass at about 17 million kilometres from Earth. The resolution achieved by combining the two radio telescope systems, Goldstone transmitting and Green Bank receiving, was described by JPL scientist Marina Brozovic as equivalent to being able to sit in Los Angeles and read a dinner menu at a restaurant in New York. At a distance of 17 million kilometres, the radar was returning data precise enough to resolve features on the surface of the asteroid at 38.75 metres per pixel. That precision allowed the orbital calculation to be updated with position measurements of extraordinary accuracy. Combined with a new determination of the Yarkovsky effect on the asteroid, a subtle force we will examine in detail in a later section, the 2021 radar data reduced the uncertainty in the 2029 approach distance from hundreds of kilometres to approximately 3 kilometres. 3 kilometres against a keyhole that was hundreds of metres wide. The 2068 keyhole cleared. The trajectory as known in 2021 would carry Apophis outside every identified keyhole by margins that the uncertainty in the calculation could not bridge. David Farnokia of the Centre for Near-Earth Object Studies announced that a 2068 impact was not in the realm of possibility anymore, and that the model showed no impact risk for at least the next 100 years. But the story of the keyhole is not finished with that announcement. It is finished with a question that the keyhole concept forces you to ask about every future close approach of any significant asteroid, not just Apophis. The 2029 flyby will permanently alter the orbit of Apophis. Earth's gravity will change the asteroid's trajectory in ways that are calculable, but whose downstream consequences extend into the future in ways that are progressively harder to resolve as the time horizon lengthens. After 2029, Apophis will be on a different orbit, and that orbit will bring it back to Earth's vicinity on a different schedule than its current orbit does. The post-2029 orbit will carry the asteroid through different gravitational interactions with different planets over different timelines, and somewhere in that extended future, there may be additional keyhole scenarios that the current models cannot identify because the data required to identify them, the precise post-2029 orbital parameters, will not exist until the 2029 flyby has actually occurred and been measured. The 100-year safety assurance issued in 2021 is real and meaningful. It is based on thorough and rigorous calculation. But it is also conditional on the current understanding of the forces acting on Apophis, an understanding that will be updated necessarily after the 2029 flyby creates a physically different asteroid on a slightly different trajectory. The question of whether there are keyholes beyond 100 years that the 2029 flyby will either route Apophis toward or away from is a question that cannot be fully answered until after the flyby has happened. This is not cause for alarm. It is cause for the kind of sustained attention that the planetary defense community has been giving to Apophis since 2004 and will continue giving after 2029. But it is also the conceptual core of why the people who study these things do not describe their work as finished when the current risk table is cleared. The table reflects current knowledge. Current knowledge changes when the universe runs new experiments, and on April 13th, 2029, the universe is going to run the most informative asteroid experiment in recorded history, right in our satellite zone, visible to 2 billion people while 3 spacecraft watch from close range. The keyholes for the post-2029 orbit of Apophis will be calculated from the data those spacecraft and those ground-based telescopes return. The universe is not done setting up the calculation. It is about to run the next measurement. That is what the God of Chaos does. It does not destroy. It introduces uncertainty, and then it waits to see what the uncertainty produces. What happens when the planet's own gravity becomes the variable that determines whether an asteroid misses forever or returns to strike? The size of Apophis is reported in almost every article and broadcast about the asteroid, and it is reported so routinely, with the same comparisons attached to it so consistently, that the number has lost its texture. 340 meters, roughly the height of the Empire State Building, 5 football fields laid end to end. These are the numbers and the comparisons that appear in coverage, and they are accurate, but they do not produce the visceral understanding of scale that the physics of what this object represents actually requires. So let us try something different. Let us build the size of Apophis from the ground up, in terms that your body can process rather than your abstract reasoning. Apophis has a mean diameter of approximately 340 meters. Its longest axis is at least 450 meters. These are not the dimensions of a sphere. Apophis is elongated. Radar imaging suggests it is dual-lobed, shaped roughly like a peanut or a contact binary, 2 regions of mass that have slowly migrated toward each other under their own weak gravity and settled into contact. Imagine holding a peanut in your hand and looking at the 2 bulges where the shell narrows in the middle. Now scale that shape up to 450 meters in length. That is the shape of the object that will pass through your satellite zone in 2029. The Empire State Building, for reference, stands at 443 meters to the roof, including the antenna. Apophis's longest dimension of 450 meters is comparable to that height. The object is taller than one of the most recognizable buildings on Earth, laid on its side and tumbling slowly end over end through space. A day on Apophis, 1 full rotation of the asteroid on its axis, currently takes approximately 30.6 hours. There is also a secondary rocking motion, a precession around the long axis, that operates on a much longer period of approximately 264 hours. Apophis does not spin cleanly. It rotates and wobbles simultaneously, a motion that planetary scientists call non-principal axis rotation. Now consider the mass. Apophis is estimated to weigh approximately 27 billion kilograms, or 30 million metric tons. The precise figure depends on assumptions about the asteroid's internal density and porosity, which are not yet well constrained by the available data. But 27 billion kilograms gives a working number. The entire steel structure of the Empire State Building weighs approximately 60,000 metric tons. Apophis contains the mass equivalent of 500 Empire State Building steel structures, compressed into a single body slightly longer than one of them is tall. The asteroid is composed primarily of silicate rock mixed with metallic nickel and iron. This places it in the classification called S-type, the stony asteroids, which are the most common variety of near-Earth object. S-type asteroids are thought to be the parent bodies of the ordinary chondrite meteorites, the most frequently recovered class of meteorite on Earth. If you have ever seen a meteorite in a museum, the brown-grey rocky kind with the crusted exterior from atmospheric entry, there is a reasonable probability it came from an object chemically similar to Apophis. The material is not exotic. It is the same rocky material that the inner solar system has been processing for 4.6 billion years. What makes it dangerous is not its composition. It is its size and its speed. At the moment of closest approach, Apophis will be travelling at approximately 7.4 kilometers per second relative to Earth. In the units that human intuition can better process, that is approximately 26,500 miles per hour. The International Space Station, orbiting at a speed of about 17,500 miles per hour, is one of the fastest human-made objects in regular operation. Apophis will be moving half again as fast as the ISS at the moment it threads the satellite zone. The energy released if an object of this mass were to strike Earth at this velocity is approximately 200 megatons of TNT. The nuclear weapon that destroyed the city of Hiroshima in 1945 yielded approximately 15 kilotons of TNT. 1 megaton is 1,000 kilotons. An Apophis impact would release 1,200 megatons, or approximately 80,000 times the energy of the Hiroshima bomb. The largest nuclear weapon ever detonated by any nation was the Soviet Tsar bomber, tested in 1961 at a yield of approximately 50 megatons. An Apophis impact would release roughly 24 times the energy of the largest nuclear test in human history. But even those numbers, enormous as they are, do not fully convey the regional scale of destruction. A 1,200 megaton impact on land would create a crater several kilometers across, generate a shockwave capable of devastating structures hundreds of kilometers from the impact site, inject enormous quantities of rock dust and vaporized material into the atmosphere, and cause fires across a wide radius around the impact point. The Planetary Society's assessment is that millions of people could die in a populated impact zone. An impact in a major metropolitan area would be a civilizational catastrophe for the affected region, comparable to nothing in the recorded history of human conflict. For comparison, the Chelyabinsk meteor that exploded over Russia in February 2013 was approximately 20 meters across. That is less than 1/20th of Apophis's mean diameter. Volume scales with the cube of a linear dimension, which means a very rough estimate of the relative volume of Apophis compared to the Chelyabinsk object is on the order of 8,000 times larger. The Chelyabinsk explosion, which occurred at high altitude and released no material that reached the ground intact, produced a shockwave that damaged buildings across a 50-kilometer radius, shattered windows in thousands of structures, and sent more than 1,500 people to hospitals, primarily with injuries from broken glass. It was the largest natural explosion in Earth's atmosphere since the 1908 Tunguska event, which itself leveled approximately 2,000 square kilometers of Siberian forest. Apophis contains several thousand times the volume of the Chelyabinsk object. At its size, it would not burn up completely in the atmosphere. A significant fraction of the mass would reach the surface. The airburst, if it disrupted before surface impact, would be at much lower altitude and much higher energy than Chelyabinsk. The consequences would be categorically different in scale from anything the 20th century produced. None of this is going to happen on April 13, 2029. The trajectory is known with sufficient precision to confirm that Apophis will not strike Earth during this flyby. But understanding what Apophis actually is, in physical terms, is the prerequisite for understanding what the 2029 passage actually means. When 2 billion people look up at a magnitude 3.1 point of light moving across the sky on a Friday evening in April, they will be looking at 27 billion kilograms of silicate and nickel iron travelling at 26,500 miles per hour, 32,000 kilometers overhead. They will be looking at something that carries enough kinetic energy to end a region. They will be looking at it with their naked eyes, without instruments. From the surface of the planet, it will just barely miss. the smallness of the light they see will be misleading in a way that the physics does not support. There is a concept in astronomy called apparent versus absolute magnitude, the distinction between how bright something looks from a given distance versus how intrinsically luminous it is. Apophis at magnitude 3.1 looks, to the naked eye, like a moderately bright star. It does not look like a civilizational hazard. It does not look like anything that should be the subject of 20 years of intensive orbital tracking and 3 dedicated spacecraft missions. It looks like a star, moving. The disconnect between appearance and reality is one of the things that makes the 2029 flyby philosophically interesting beyond its scientific value. The object that defined a generation of planetary defense thinking, that occupied the top of the impact risk table for 17 years, that generated more careful orbital calculation than any other near-Earth object in history, will be visible to 2 billion people as a slowly moving point of dim light that most of them will need to be told to look for. The mass that can end a city looks, from 32,000 kilometers away, like a star. This is, in its way, the most important lesson the 2029 flyby teaches. Not about Apophis, about the nature of hazard in a universe that does not arrange its threats in ways our senses were evolved to detect. Everything that has ever threatened human civilization from beyond the atmosphere has looked, until the moment of arrival, like a star, or like nothing at all. What changes about the way a civilization thinks about itself when it watches the threat walk by in plain sight? For the scientists studying Apophis, the 2029 flyby is not a crisis averted. It is not a near miss to be catalogued and moved past. It is something that the scientific community has been building toward for 20 years of observation, mission planning, and international coordination, and what they have built toward is an opportunity that the solar system has, through the completely indifferent operation of orbital mechanics, arranged on a schedule that defies any reasonable expectation of scientific luck. Patrick Michel, Director of Research at the CNRS at the Observatoire de la Côte d'Azur in Nice, and one of the lead scientists for ESA's Ramses mission to Apophis, described the situation in language that is worth quoting precisely, because it captures something that no amount of technical explanation quite conveys. He said that for the first time ever, nature is bringing one to us and conducting the experiment itself. All we need to do is watch as Apophis is stretched and squeezed by strong tidal forces that may trigger landslides and other disturbances and reveal new material from beneath the surface. Nature is bringing one to us and conducting the experiment itself. That sentence describes something genuinely unprecedented in the history of asteroid science. Every asteroid mission ever flown has required a spacecraft to travel significant distances through the inner solar system to reach its target. The OSIRIS-REx mission, which collected samples from the asteroid Bennu and returned them to Earth in 2023, required a 7-year journey. The Hayabusa missions by the Japan Aerospace Exploration Agency required years of transit to reach their targets. The New Horizons mission to Arrokoth, the distant Kuiper Belt object that may resemble the building blocks from which planets formed, required more than a decade of flight. Studying asteroids up close has always meant going to them, with all the engineering complexity and cost and risk that implies. In April 2029, Apophis will come to the vicinity of Earth on its own schedule, carrying with it all the properties of a significant near-Earth object, and pass close enough to be studied in extraordinary detail by instruments both in space and on the ground. The physical changes that the flyby will produce on Apophis are what make this a natural experiment rather than simply a spectacular observation. When a body as massive as Earth exerts gravitational force on a body as small as Apophis, the force is not uniform across the asteroid. The side of Apophis nearest Earth during the flyby will be pulled toward our planet more strongly than the side facing away. The gradient of gravitational force across the diameter of the asteroid, stronger on the near side and weaker on the far side, is what physicists call a tidal force, using the same language applied to the forces that create ocean tides on Earth through the Moon's gravitational influence. Tidal forces on a rocky body without liquid produce mechanical stress. The near side is being pulled one way, and the far side is being pulled less in the same direction, which creates internal tension across the structure of the object. If the object is rigid and structurally coherent, it resists this stress. If the object is a rubble pile, a loosely bound collection of fragments held together primarily by its own weak self-gravity rather than by the internal strength of a solid rock, the response to tidal stress is different. Apophis is understood to be a rubble pile. It is not a monolithic solid rock. It is a collection of boulders, gravel, and dust that have accumulated together under their own gravity over a long history of slow collisions and gravitational settling. The internal structure is thought to resemble the inside of a loosely packed gravel bed more than the interior of a solid stone sphere. There are voids and variable density regions throughout. The cohesion is primarily gravitational rather than mechanical. When tidal forces act on this kind of structure during the 2029 flyby, the effects are not easily predictable in their details, which is precisely what makes them scientifically valuable. Simulations run by planetary scientists estimate that approximately half an hour before Apophis reaches its closest point to Earth, the tidal stress in certain regions of the asteroid will exceed the cohesive force holding the loose surface material in place. Approximately 1% of the asteroid's surface is estimated to be disturbed during the flyby. Boulders that have rested in fixed positions for millions of years will shift. Dust and fine-grained material that accumulated on the surface through long exposure to the space environment will redistribute. In the local gravity field of the asteroid, this constitutes something like a landslide, exposing material from beneath the weathered outer layer that has not been touched by solar radiation in a very long time. The surface of any asteroid that has existed in space for millions of years is not the same as its interior. Solar radiation, micrometeorite impacts, and thermal cycling between the day and night sides produce a weathered outer layer called regolith, similar in concept to the soil on Earth, but formed by different processes without any chemistry of life or water. Beneath this weathered surface layer is material that has been protected from these processes, material that retains chemical and physical properties more representative of the asteroid's original composition. The tidal disturbance of the 2029 flyby will, in locations where the stress is sufficient, overturn this arrangement and expose fresh subsurface material to direct observation. A spacecraft at Apophis, during or immediately after the flyby, will have an unprecedented opportunity to compare the weathered surface chemistry with the fresher material that the event exposes. This comparison directly informs one of the central questions in asteroid science: how the surface properties of asteroids that have been exposed to the space environment for long periods differ from the properties of the underlying material, and what that means for interpreting spectral observations of asteroid surfaces. The rotation of Apophis will also change during the flyby. The current rotation period of approximately 30.6 hours, one Apophis day, will be altered by the tidal interaction. The amount and direction of the change depend on the specific geometry of the asteroid's orientation relative to Earth during the flyby, parameters that cannot be fully determined in advance. The secondary rocking motion, the 264-hour precession around the long axis, will also be affected. The outcome is that after the 2029 flyby, Apophis will spin differently than it does today, and will continue to spin differently for the rest of its existence. The changes to the rotation state will be permanent. The changes to the orbit will be permanent. The surface modifications will be permanent in the sense that the landslides and redistributions that occur during the flyby will remain visible in the surface morphology until the next significant event modifies them. Apophis will carry the gravitational fingerprint of Earth's 2029 intervention in its physical structure for billions of years. 3 spacecraft are being coordinated to observe and document this transformation. NASA's OSIRIS-APEX, the repurposed version of the OSIRIS-REx spacecraft that successfully collected samples from the asteroid Bennu and returned them to Earth in 2023, is currently en route to Apophis. OSIRIS-REx was renamed OSIRIS-APEX for origins, spectral interpretation, resource identification, and security Apophis Explorer, when its mission was extended after the Bennu sample delivery. The spacecraft will use Earth's gravity during the April 2029 flyby as a gravity assist to change its own trajectory and catch up to Apophis. It will arrive at the asteroid approximately 2 months after the closest approach and begin an 18-month campaign of close-range investigation. ESA's Ramses mission, the Rapid Apophis mission for space safety, is designed specifically to arrive at Apophis before the flyby in February 2029, 2 months before the closest approach, to establish a detailed baseline measurement of the asteroid's properties before Earth's gravity begins to alter them. The mission was approved at ESA's Ministerial Council meeting in November 2025 and requires launch in April 2028 to make the arrival window. Ramses will observe Apophis during the flyby itself, at close range, documenting in real time the changes that Earth's tidal forces produce. When OSIRIS-APEX arrives in June 2029, the two missions together will have a before, during and after record of the same physical event. JAXA's Destiny plus spacecraft, originally targeted at a different asteroid, will also contribute observations during the Apophis encounter. This international coordination, 3 spacecraft from 2 space agencies plus a third from a third, converging on a single asteroid to document a single event, reflects the level of scientific significance that the planetary defense and asteroid science communities have attached to the 2029 flyby. It does not happen often in space science that all the relevant parties agree simultaneously that a specific target at a specific moment is worth this level of collective resource investment. The reason they all agree is that what Apophis is about to experience, what Earth's gravity is going to do to it as it passes through the satellite zone, has never been observed before in the history of scientific observation of the solar system. We have theoretical models of how rubble pile asteroids respond to tidal stress. We have computer simulations. We have inferences from the surface morphology of asteroids that have experienced close approaches in the more distant past. But we have never watched it happen, in real time, with instruments capable of resolving individual boulders on the surface. April 2029 is when watching becomes possible. The natural experiment that orbital mechanics arranged over billions of years of solar system evolution will run its course in a matter of hours. The data from those hours will be studied for decades. What happens when you watch the universe reshape an asteroid in real time? That is the question that has 3 spacecraft on their way to find out. When NASA announced in March 2021 that Apophis poses no impact risk for at least 100 years, the phrasing was precise and deliberate in ways that are easy to miss if you are reading quickly. Not forever. Not beyond all foreseeable concern. Not cleared from the books permanently. For at least 100 years. The qualifier is doing real work in that sentence, and understanding what work it is doing is the key to understanding what the 2029 flyby actually means for the long-term trajectory of this particular piece of the solar system. The 100-year safety assessment is based on the best currently available orbital solution for Apophis, which incorporates all observations made through March of 2021, including the high-resolution radar data from Goldstone and Greenbank. That orbital solution predicts, with an uncertainty now measured in a few kilometers at the 2029 approach, where Apophis will be during the flyby, and from that position the subsequent trajectory can be calculated forward in time. Over the next 100 years, no point in that calculated trajectory places Apophis on a collision course with Earth, but the 2029 flyby will permanently alter the orbit, and the altered orbit will carry the asteroid through a different set of future interactions with Earth and other planets than the current orbit does. The models can project forward from the predicted post-2029 orbit, but the predicted post-2029 orbit is derived from the predicted 2029 approach geometry, and that geometry carries residual uncertainties that only direct observation during and after the flyby can fully resolve. There is also the question of the Joukowsky effect, which we will examine in detail in a later section, and which is one of the reasons the 100-year safety assessment is bounded by time rather than stated as permanent. The Joukowsky effect depends on properties of the asteroid that will be partially modified by the 2029 flyby. The measurement of the Joukowsky effect conducted before 2029 will need to be updated afterward, using the new spin state and new orbital parameters, before the long-term trajectory beyond the current century can be computed with confidence. The 100-year window is therefore not an expression of complacency. It is an honest description of the time horizon over which the current models are reliable. Beyond that horizon, the uncertainties compound in ways that require new data to resolve. The new data will come from the 2029 flyby and the spacecraft that observe it. But there is a separate question about the 100-year assessment that came from an unexpected direction in 2024, and it deserves careful handling because the numbers involved are small, but the underlying physics is real. Astronomer Paul Wiegert of the University of Western Ontario published a paper in which he examined a possibility that had not been prominently discussed in public coverage of Apophis's risk profile. The question he asked was whether the asteroid could be struck by a smaller undetected object during the period between 2021 and 2027, when Apophis is too close to the Sun in the sky to be observed from Earth. This window of observational invisibility, when the asteroid is behind the Sun from Earth's perspective and cannot be tracked by ground-based telescopes, creates a gap in our knowledge of the asteroid's exact position that will only close when Apophis reappears in the observable sky in 2027. During this gap, the asteroid is flying through a region of space that is not empty. The inner solar system contains a substantial population of small objects, meter-class and smaller, that impact Earth itself several times per year. Most of these go undetected until they enter the atmosphere. A small fraction of them are found in advance by survey telescopes, but the overall detection completeness for objects below roughly 50 meters is very low. Apophis, as it traverses its orbit, passes through the same population of small objects that occasionally strikes Earth. Vigert's calculation examined the probability that one of these undetected small objects could collide with Apophis during the observational gap. The size of impactor that matters for this analysis is not the kind that could destroy the asteroid, which would require something much larger. The relevant impactors are ones large enough to deliver a detectable impulse to Apophis's trajectory, a nudge that would shift its predicted 2029 approach position relative to the gravitational keyholes. The probability Vigert calculated was approximately 1 in a million. 1 in a million over the full period of the observational gap. That is a very low probability. It is, by any reasonable standard, not something to treat as a significant concern from a risk management standpoint. 1 in a million events are real events that happen somewhere in the universe constantly. But for any given system, they are not things that planning frameworks are typically built around. However, the existence of this probability means that the 2029 approach trajectory cannot be treated as perfectly known from 2021 data alone. When Apophis reappears in the observable sky in 2027, the first priority of the planetary defense tracking community will be to take new measurements and update the orbital solution. If a small undetected impactor had altered Apophis's trajectory during the gap, the 2027 observations would reveal this through a discrepancy between the predicted and observed positions. If the trajectory is confirmed to be consistent with the 2021 prediction, the keyhole scenarios can be ruled out with increased confidence. The observational gap is a window not of risk but of reduced certainty. The community knows this. The response infrastructure is ready for the 2027 reappearance observations, and the probability that anything concerning will be found is very low. But the fact that the question can be asked at all, that the trajectory of an asteroid we have been tracking since 2004 is subject to uncertainty from undetected small body interactions during a window when we cannot observe it, is a reminder of something fundamental about the planetary defense enterprise. We are tracking the objects we know about. The solar system contains many more objects we do not. The known catalogue provides the tracking community with a clear picture of the large hazard landscape. But the small body population that it cannot fully track creates a background of potential perturbations that operate below the resolution of any survey. Apophis is large enough that those perturbations are almost certainly too small to produce a trajectory change large enough to matter, but the question of whether they can be confirmed to be too small requires the 2027 observations that the gap prevents. The 100-year safety assessment and the question of what happens after 100 years are ultimately not questions about Apophis specifically. They are questions about the nature of predictability in a solar system that contains more objects than any survey has ever catalogued, all of them subject to forces that must be measured continuously to be understood. The asteroid science community tracks Apophis not because it is dangerous. It tracks Apophis because Apophis has taught the community, over 20 years of observation, more about the practice and limits of asteroid orbit prediction than any other single object in the catalogue. The lessons learned from watching Apophis have improved the methodology applied to every other potentially hazardous object in the database. After 2029, that teaching will continue. The post-flyby Apophis on its new orbit, with its new spin state, with its updated Yarkovsky parameters, will become the best characterized near-Earth asteroid in the catalogue. The 25 years of observation from 2004 to 2029 will be extended by the close-range data from OSIRIS, APEX, and RAMSES, creating a dataset of unprecedented richness for a single object. Every future impact risk assessment for S-type asteroids will be grounded, in part, in what is learned from Apophis between now and 2029, and in the years of study that follow. This is what a 100-year safety horizon actually means in the context of planetary defense. It does not mean the problem of Apophis is closed for a century and can be set aside. It means the problem of Apophis is producing knowledge that will be applied to every other asteroid in the system for a century. The productivity of that knowledge production is one of the strongest arguments for the value of the planetary defense enterprise as a whole. The god of chaos turns out to be one of the most useful teachers the solar system has ever offered. Not because it threatened us, though it did, because the process of determining that it would miss us produced a body of methodology and measurement and understanding that makes the next candidate on the risk table easier to assess. What does an asteroid teach you that a century of safe nights never could? The scientific excitement surrounding the 2029 Apophis flyby cannot fully be separated from the planetary defense question that runs underneath all of it. These are not distinct conversations happening in parallel. They are the same conversation, viewed from two slightly different angles. One angle is curiosity, the other is preparation. Both lead to the same data, collected by the same spacecraft, processed by the same scientists. To understand why the 2029 flyby matters for planetary defense beyond the immediate question of whether Apophis itself will hit Earth, you have to start with the classification of the asteroid. Apophis is an S-type asteroid, composed primarily of silicate rock mixed with metallic nickel and iron. This chemical composition places it in the most common class of near-Earth objects, the stony asteroids. Approximately 75% of all near-Earth objects that have been classified spectroscopically are either S-type or related stony variants. S-type asteroids are the most abundant class of potentially hazardous objects in the catalogue. The DART mission, conducted by NASA in collaboration with ESA and launched in 2021, demonstrated in September 2022 that a kinetic impactor can measurably alter the orbit of an asteroid. The spacecraft deliberately collided with Dimorphos, the small moonlet of the binary asteroid Didymos, and changed Dimorphos's orbital period by approximately 33 minutes. This was significantly more deflection than pre-impact models had predicted. The additional deflection came from ejecta, the material thrown off the surface of Dimorphos by the impact, which carried momentum in the opposite direction to the impactor and amplified the total momentum transfer. The ejecta plume was studied by ESA's Hera mission, which arrived at the Didymos system in 2024 to assess the aftermath of the DART impact. The DART mission was an extraordinary achievement and a landmark in the history of planetary defense. Humanity demonstrated for the first time that it could physically alter the orbit of a small body. The technique works, the physics is confirmed. If an asteroid were found on a collision course with Earth with sufficient warning time, kinetic impactor technology would be available as a deflection option. But Dimorphos and Didymos are C-type asteroids, carbon-rich bodies with physical properties substantially different from S-type stony asteroids. The ejecta amplification factor measured at Dimorphos, the ratio of total momentum transferred to the momentum carried by the impactor alone, depends on the internal structure of the target body, its porosity, its surface strength, the way loose material behaves when subjected to the hypervelocity impact. These properties are different for C-type and S-type asteroids in ways that the theoretical models capture imperfectly. If the most common class of potentially hazardous asteroid is S-type, and the only kinetic impactor test we have was conducted on a C-type target, then the calibration of our deflection models for the most likely threat category is missing a critical data point. The DART experiment tells us that kinetic impactors work on C-type targets. It does not tell us, with comparable precision, how they would perform on S-type targets. Apophis provides the opportunity to begin addressing this gap. OSIRIS-APEX, which will study Apophis in close detail for 18 months after the 2029 flyby, will characterize the physical properties of an S-type rubble pile asteroid to a degree that has never before been achieved. The surface strength, the grain size distribution of the regolith, the porosity of the bulk material, the response of the surface to the tidal disturbance of the flyby, the distribution of boulders and fine material, all of these properties are inputs to the models that calculate how an S-type asteroid would respond to a kinetic impactor. OSIRIS-APEX will conduct what is called a STIR maneuver, spacecraft thruster investigation of regolith, in which the spacecraft fires its thrusters directly at the surface of Apophis from a very close range, roughly 5 meters, to excavate material from the upper surface layer and expose the subsurface below. The ejecta produced by this maneuver will be analysed by the spacecraft spectrometers, providing composition data on material that has not been exposed to the space environment before. This is a small-scale analogue to what a kinetic impactor would do to a larger target, and it will produce data directly relevant to understanding how S-type material behaves under energetic disturbance. ESA's Ramses mission adds the dimension of before and after comparison. By arriving at Apophis in February 2029 and conducting a thorough survey before the Earth flyby, Ramses establishes a baseline that documents the asteroid's properties in their undisturbed state. After the flyby alters the spin state, reshapes the surface in some locations, and changes the orbital parameters, the post-flyby surveys by both Ramses and Osiris Apex can quantify exactly what changed and how much. This comparison is a dataset that planetary defense modelers have never had access to before, a before and after record of how a rubble pile asteroid responds to a significant external force. The significance for deflection planning is direct. If a planetary defense mission were authorized to deflect an S-type potentially hazardous asteroid using a kinetic impactor, the mission designers would need to know how much ejector the impact would produce, and in what directions, how the momentum transfer would be amplified relative to the impactor momentum, and whether the structural response of the asteroid to the impact would be coherent, or whether it might fragment. The data from the Apophis flyby and the subsequent Osiris Apex investigation will provide the highest resolution characterization yet available for this class of object. There is also a lesson in the process of tracking Apophis that applies to planetary defense more broadly, independent of any physical data from the flyby itself. When Apophis was discovered in 2004, and its initial high-impact probability was calculated, there was no established international protocol for what to do next. There was no agreed procedure for notifying governments, no established communication framework for managing public concern, no international coordination body with clear authority to recommend action. The planetary defense community was operating on procedures developed piecemeal from previous experience, with objects that never generated impact probabilities anywhere near as high. The response to Apophis in 2004 and the subsequent years of tracking built those frameworks. The International Asteroid Warning Network, which coordinates asteroid observations and impact risk assessments among observatories and agencies around the world, owes its current form in part to the institutional evolution that Apophis accelerated. The Space Mission Planning Advisory Group, which coordinates potential deflection mission responses across international space agencies, was similarly shaped by the Apophis experience. The procedures now in place for escalating from detection to assessment to notification to potential response reflect lessons learned from managing the public and institutional response to the most alarming near-Earth object ever discovered. None of these institutional developments are visible in any single observation of Apophis. They are embedded in the systems that will respond to the next significant asteroid, the one that has not yet been discovered, the one whose first probability estimates may be higher than 2.7% and may not come down as cleanly as Apophis's did. The 20-year period of tracking and response planning that Apophis initiated has produced a global asteroid defense infrastructure that is substantially more capable than anything that existed before June 2004. This is the other impact Apophis has had, not a physical impact which will not happen, but an institutional one, which has already occurred and has already made the planet more capable of responding to the next candidate on the risk table. Whatever that next candidate turns out to be, it will be assessed with better tools, better procedures, and better international coordination than was available when Apophis was first found. The God of Chaos, in its long, slow approach across the inner solar system, has been teaching the people watching it how to protect the planet it is aimed at. That is an extraordinary outcome from 20 years of professional anxiety about a rock. What does it mean to build a defense before you know what you are defending against? On the evening of April 13th, 2029, if the sky above your location is dark and clear and you happen to be in the right part of the world, you will be able to step outside, look up, and see Apophis with your naked eye. It will not look like what you might expect from a description of the event you have been given. It will not look dramatic. It will not look threatening or strange or in any way distinguishable from the other points of light in the sky, except for one property. It will be moving. Visibly, slowly, clearly moving, against the fixed background of the stars. A point of light at approximately magnitude 3.1 at peak brightness, comparable in apparent luminosity to a moderately bright star in a familiar constellation, sliding steadily across the sky in a direction and at a speed that makes it unmistakably not a star. The observers who will be watching this from Europe Africa, and Western Asia will be doing something that no human beings in the full recorded history of our species have done before. They will be watching, with the unassisted human eye, an asteroid the size of a skyscraper passing through the space between the surface of the Earth and the ring of machines that carry civilization's communications. They will be watching this from the surface of the planet that the asteroid is threading past. They will be watching it with eyes that evolved for foraging and socializing and threat detection in an environment that contained no context for what they are looking at. The experience will be real and simultaneously incomprehensible in the way that all large-scale astronomical phenomena are incomprehensible to a nervous system calibrated for distances you can walk in an afternoon. The path that Apophis will trace across the sky during the hours it is visible is calculable to high precision. The asteroid will move from the constellation Centaurus in the southwest, tracking northward and westward through the sky, rising to Perseus in the northern regions, and then sweeping southward toward Pisces in the southeast. Over the course of the full observable window, it will cover an arc of approximately 205 degrees. For any given observer at a fixed location, the visible portion of this arc will depend on the horizon, on light pollution, on the time of local sunset. From a dark location in Central Europe, observers will see Apophis moving for several hours, the star-like point tracing a visible track against the background of the fixed stars. The angular velocity at peak will be high enough to be perceptible over the course of a few minutes of watching. Not dramatic, not the kind of motion that registers as alarming in a few seconds of glance, but deliberate, steady, observable. A thing moving in a sky where everything else is stationary. The brightness will peak at magnitude 3.1. To give that a reference, the stars of the Big Dipper range from approximately magnitude 1.8 to 3.3. Polaris, the North Star, is approximately magnitude 2.0. At peak, Apophis will be somewhat fainter than Polaris but brighter than the faintest stars of the Big Dipper. A person with no knowledge of what to look for, encountering the asteroid's light without context, would think they were seeing a somewhat unremarkable star in the wrong part of the sky, moving. The fact that it is moving is everything. Stars do not move on the timescale of minutes. Planets move, but on the timescale of nights and weeks. An object moving visibly across the background of stars on the timescale of minutes is the signature of something very close by in astronomical terms. No other phenomenon in the common night sky produces that signature for an object of this apparent brightness. Anyone who sees it and understands what they are seeing will know immediately that this is not a star. Approximately 2 billion people live in the regions from which Apophis will be visible to the naked eye during the 2029 flyby. Europe has a population of roughly 750 million. Africa has a population of approximately 1.4 billion. The parts of Western Asia that fall within the visibility zone add hundreds of millions more. 2 billion human beings spread across more than a dozen time zones, speaking hundreds of languages, living under governments with widely varying relationships to scientific communication and public information, will have the physical opportunity to look up and see this. The cultural response to that experience will not be uniform. In regions with strong scientific literacy and active science communication, the event will have been anticipated with excitement. Educational programs will have prepared people for what to look for and how to process what they see. Planetariums and astronomy clubs and science communicators will have been building toward this moment for years. The 2 billion witnesses in these regions will encounter Apophis with context. In other regions, the encounter will occur without institutional preparation, filtered through whatever local frameworks are available for making sense of a moving star that does not belong in the sky. Folklore, religion, social media. Whatever the local equivalent of word of mouth, carries to people who do not have access to astronomy education. These 2 billion witnesses will experience the same visual event as their better prepared counterparts in Europe, and they will interpret it through completely different lenses. There is a history to public responses to unusual astronomical events that offers some guidance for what 2029 might produce. The 1997 appearance of Comet Hale-Bopp generated a wide range of responses. For most observers, it was a beautiful and memorable sky event with no lasting impact on behaviour. For a small group in California, the comet's appearance was interpreted as the signal for a mass suicide that ended 39 lives. The interpretation of the comet by Heaven's Gate was an extreme outlier, but it illustrates a real dynamic. Astronomical events that have no routine precedent in human experience do not arrive into a cultural vacuum. They arrive into a landscape of existing beliefs, fears, and frameworks that will shape how they are understood. Apophis will be visible for hours, moving across half the sky, bright enough to see without instruments, unprecedented in the experience of every person who watches it. The overwhelming majority of the 2 billion witnesses will see it, be awed or indifferent and go about their lives. But the cultural moment of 2 billion people simultaneously confronted with visible evidence that the solar system contains large rocks moving through the space overhead, rocks that have been calculated and assessed and tracked for 25 years, rocks that have names and histories and planetary defense missions devoted to them, is a moment without historical precedent. What does it do to a civilization's relationship with the sky when the sky produces something that everyone can see, that science has been telling people to expect, and that arrives exactly when and where the calculations predicted? The answer may be more consequential than any data collected by Osiris Apex or Ramses, because the data changes what planetary scientists know about S-type asteroids. But the sight of Apophis crossing the sky above 2 billion people changes what 2 billion people understand about the neighbourhood they live in, and changes in understanding at that scale are the foundation of changes in political will, in resource allocation, in the institutional support for the work that planetary defence requires. Every dollar ever appropriated to planetary defence programs, every professional career dedicated to asteroid tracking, every mission ever flown to characterise a near-Earth object, was funded by political systems that represent populations of people who did not have a visceral, lived understanding of why the work mattered. Those populations were told why it mattered. They read about it, they encountered it abstractly. Some of them were persuaded and some were not, and the funding levels for planetary defence have historically reflected the gap between the intellectual argument for the work and the felt urgency that drives political action. After April 13th, 2029, the 2 billion people who live in the visibility zone of the Apophis flyby will have had an experience. Not an argument, an experience. They will have looked up at the sky they look at every night and seen something moving through it that was not there the night before and will not be there the night after. Something large, something tracked for a quarter century, something that the same science that predicts its path also tells them will miss them this time. This time. The political conversation about planetary defence after 2029 will happen in a world where 2 billion of its 8 billion people have seen an asteroid with their own eyes. That is a different conversation from any that has occurred before. What changes when the sky stops being background scenery and becomes something you have to pay attention to? Apophis is remarkable for exactly one reason that has nothing to do with its size, its composition, its orbital characteristics, or its 2029 trajectory. Apophis is remarkable because we found it. This sounds like a trivial observation until you examine what finding it required and what finding it means in the context of the broader population of near-Earth objects that we have not found. The discovery of Apophis in 2004 was not the product of a targeted search for this specific object. It was the incidental result of a systematic sky survey conducted at the Kitt Peak National Observatory, a program designed to sweep the sky repeatedly and flag anything that was moving. Roy Tucker, David Tholen, and Fabrizio Bernardi were not looking for Apophis. They were executing a process, and the process caught it. That process, and the hundreds of similar processes running at observatories around the world in 2004, had detection completeness that was not uniform across all possible asteroid sizes and orbital configurations. Large asteroids are easier to detect than small ones. Asteroids that approach from the night side of Earth are easier to detect than those that approach from the direction of the Sun, because the survey telescopes are pointed at the dark sky and cannot look into the solar glare. Asteroids on certain orbital geometries can remain in the catalogue gaps for a long time, visible in principle but not observed in practice, because the survey cadence has not turned in their direction at the right moment. The asteroid tracking system that exists today has made extraordinary progress in the 50 years since systematic surveys began. NASA's current estimates of the near-Earth asteroid population and the completeness of the catalogue at different size thresholds provide the clearest picture of the planetary hazard landscape that has ever existed. At sizes above 1 kilometre, asteroids large enough to produce global effects if they strike Earth, the catalogue is estimated to be approximately 95% complete. Roughly 19 out of every 20 asteroids in this size class are known. Their orbits are tracked, their trajectories are calculated. None of them are currently on a collision course with Earth. The civilizational hazard from kilometre-scale objects is, given current knowledge, very well characterized. Below 1 kilometre, the picture changes, in the size range from 140 meters to 1 kilometre, sometimes described as the city killer range because objects in this class could devastate a metropolitan area without producing the global effects of a larger strike. The catalogue is estimated to be approximately 40% complete. This means roughly 60% of all potentially hazardous asteroids in this size class are currently unknown. They exist. They are out there, following their orbital paths through the inner solar system, some of them on trajectories that will eventually bring them close to Earth. They are simply not yet in the database. Apophis, at 340 meters, sits at the upper end of this uncatalogued majority. It was found because it made a moderately close approach to Earth in 2004 that put it within range of the survey telescopes. Before that approach, it was invisible to the existing surveys. It had been following its orbit for the 4.6 billion years of the solar system's existence without any human instrument being sensitive enough or pointed in the right direction to detect it. The detection system worked when the geometry of the orbit brought Apophis close enough to be caught. But the vast majority of the objects in the same size class, those that have not yet approached closely enough, remain undetected. Below 140 meters, the situation is more difficult still. Objects in the size range of the 2013 Chelyabinsk meteor, approximately 20 meters, are catalogued at a tiny fraction of their estimated population. The Chelyabinsk object arrived from the direction of the Sun, approaching from a blind spot in the survey coverage, and was not detected in advance by any telescope in the world. The first announcement that it had entered the atmosphere came from the shockwave damage to buildings and the videos captured by dashboard cameras in the Russian city below. This was not a failure of specific competence or institutional neglect. It was the fundamental detection limit of a survey system designed for larger objects, confronted with an object that approached from the one direction it could not cover. The Vera C. Rubin Observatory, currently completing commissioning at its site in the Andes Mountains in Chile, and expected to begin full operations in the next few years, is designed to dramatically accelerate the completion of the near-Earth asteroid catalogue. Its primary mirror spans 8.4 meters, making it one of the largest survey telescopes ever built. Its camera covers a field of view of 9.6 square degrees, enabling it to image large swaths of sky in a single exposure. It operates on a cadence designed to revisit every accessible portion of the sky every few nights, providing the repeated observations needed to identify moving objects against the background of fixed stars. The projected contribution of the Rubin Observatory to near-Earth asteroid discovery is substantial. Estimates suggest it will identify tens of thousands of previously unknown near-Earth asteroids in its first years of operation, including many in the size range that is currently underrepresented in the catalogue. The rate of new discoveries will peak in the early years of the survey, and then gradually decline as the catalogue approaches higher completeness levels. The survey will eventually provide the best characterized picture of the near-Earth object population in history. But the discovery flood the Rubin Observatory will generate also creates a challenge that the planetary defense community is actively working to manage. When tens of thousands of new near-Earth objects are identified, each one requires a follow-up observation campaign to determine whether its orbit brings it close enough to Earth to be considered potentially hazardous, and if so, to refine the orbit enough to make a reliable impact probability assessment. The initial orbital solution for a newly discovered object, based on the first few observations over a short arc, is rough. The uncertainty in the trajectory can be large enough that many different possible orbits are consistent with the data, some of which may include Earth impacts in the near future, and some of which may not. Only additional observations taken over days or weeks or sometimes months can distinguish between these possibilities. This is the situation Apophis was in when it was first discovered. The initial orbital solution was consistent with a set of trajectories that included a 2.7% impact probability in 2029. That probability dropped as more observations were collected, and the orbital solution was refined. The process worked correctly and produced the right answer. But it required sustained attention, dedicated observing time, and careful analysis over a period of weeks. For a single object, this is manageable. For tens of thousands of new objects being discovered simultaneously by the Rubin Observatory, the demand on follow-up observation resources becomes a coordination challenge. The International Asteroid Warning Network and the planetary defense community are preparing for this challenge. Protocols for prioritizing which newly discovered objects receive the most urgent follow-up attention, based on initial orbital characteristics and apparent size, are being developed and tested before the Rubin survey begins in earnest. The goal is to ensure that no potentially hazardous object remains in a poorly characterized orbit long enough to become a surprise. Apophis was the best possible case for this process. 25 years of warning time before the closest approach, a discovery proximity that gave the tracking community years to accumulate observations before the impact probability question became urgent, an orbital geometry that allowed frequent additional observations over the subsequent years. The result was a thorough and confident impact probability assessment. The worst case would be an asteroid similar in size to Apophis that is not found until 2 years before its closest approach. 2 years of warning time for a 340-meter potentially hazardous asteroid is not enough time to mount a kinetic impactor deflection mission. The development, launch preparation, and transit time for such a mission, based on current technology and operational experience, requires at minimum several years and more realistically closer to a decade for an asteroid at the size and orbital geometry of Apophis. An asteroid found 2 years before its closest approach in the City Killer size class is an asteroid for which the response options are limited to prediction of where it will strike and preparation of the affected region. The Rubin Observatory will reduce the probability of this worst case by catching more objects earlier in their orbital careers when the approach is still years or decades away. It will not eliminate the worst case entirely, because the survey geometry still has blind spots near the Sun, and because the small object population is too numerous for any survey to achieve complete coverage at the smaller size scales. But it will substantially improve the odds that any significant future impactor is found with enough time to do something about it. Apophis, found in 2004 with 25 years of lead time, is the system working as intended. The system will work better after 2029, when Rubin has been operating for several years, and the catalogue completeness at the 140 meter to 1 kilometer range has improved from 40% towards something higher. But the system will never be perfect. The solar system contains more rocks than any catalogue can fully enumerate, and some of them will always be in the gaps. What the existence of those gaps means, what it means to live on a planet embedded in a population of objects that are largely uncatalogued in the hazardous size range, is a question that the 2029 Apophis flyby will make visible to 2 billion people in a way that technical reports and press releases never have. The asteroid they will see crossing the sky is one that the system found with decades to spare. The ones they will not see that night are the reason the system needs to keep looking. What do you do with the knowledge that you can see some of the rocks but not all of them? There is a force acting on Apophis right now that your instruments cannot directly observe. No telescope or radar system has ever measured it by seeing it operate. It must be inferred from the slow accumulation of positional measurements over years and the statistical process of comparing where the asteroid was predicted to be against where it was actually found, and computing from the discrepancy, the magnitude and direction of the force that produced the difference. This process takes years of patient observation. The force that results from it is tiny, barely perceptible in any individual measurement, but it accumulates continuously over time in the way that a very light push, sustained for long enough, can move something very heavy a significant distance. It is called the Yarkovsky effect, named for Ivan Osipovich Yarkovsky, a Polish civil engineer working in Russia who published a private pamphlet around the year 1900 describing his hypothesis that the heat emitted by a rotating body in space would exert a small but measurable force on that body's orbit. Yarkovsky's pamphlet was printed in a very small number of copies. It did not circulate in the scientific community. It was largely forgotten for decades. Yarkovsky died in 1902 before any of the relevant calculations could be verified. His name might have vanished entirely from the history of science if a Finnish astronomer named Raimo Mäkinen had not found a reference to the pamphlet in the 1950s and brought it back to wider attention. The physics Yarkovsky described is the following. The Sun heats the sunlit side of an asteroid. As the asteroid rotates, the heated side turns away from the Sun and into shadow. The material on that side does not cool instantly. It radiates its stored thermal energy as infrared radiation for some time after rotating into shadow, and the direction it radiates is the direction the rotation carried it, which is now away from the Sun, roughly opposite to the direction the asteroid came from. The emission of infrared photons carries momentum. That momentum is transferred to the asteroid in the opposite direction. The net result is a continuous small thrust that either accelerates or decelerates the asteroid's orbital velocity, depending on whether the asteroid's spin causes the night side to face forward or backward along the orbit. The magnitude of this effect for any specific asteroid depends on multiple variables. The rotation rate determines how much time elapses between sunlit heating and the radiation of that heat into shadow. A faster rotating asteroid cools more quickly before the heated face turns away from the sun, reducing the asymmetry of the thermal emission. The composition and surface properties of the asteroid determine how quickly it heats and cools, the thermal conductivity and heat capacity of the material. The size of the asteroid matters because the ratio of surface area to mass decreases as the object gets larger, making the effect relatively smaller for larger bodies. The orientation of the spin axis relative to the orbital plane determines whether the Yarkovsky force accelerates or decelerates the orbital motion, and at what magnitude. For Apophis specifically, measurements conducted by David Tholen at the University of Hawaii and Davide Farnocchia at JPL in March 2020, using high-precision astrometric observations from the Subaru telescope and other facilities, determined that the Yarkovsky effect is causing the asteroid's semi-major axis to shrink by approximately 170 meters per year. This means the orbital period of Apophis is shortening slightly, year over year, because of the thermal re-radiation of absorbed sunlight. The effect is tiny in the context of the asteroid's full orbital path around the Sun, which has a semi-major axis of approximately 0.92 astronomical units. But it is not zero, and over decades it accumulates to an orbital displacement that matters for impact risk assessment. The reason the Yarkovsky measurement was so critical to the final confirmation of Apophis' safety is that the gravitational keyholes are small targets. The 2068 keyhole that remained in the probability calculation after the 2036 possibility was eliminated was approximately 2 meters wide in the relevant parameter space. The question of whether Apophis would pass through that keyhole during the 2029 flyby was equivalent to asking whether the asteroid's actual position in 2029 would fall inside or outside a 2-meter wide band, when the uncertainty before the Yarkovsky measurement was incorporated was hundreds of kilometers. When you measure the Yarkovsky effect and incorporate it into the orbital solution, you do two things simultaneously. You improve the prediction of where the asteroid will be in 2029, because you now have a better model of all the forces acting on it, and you reduce the uncertainty in that prediction, because the unexplained discrepancy between the model and the observations was itself a source of uncertainty that the Yarkovsky measurement resolves. The 2020 Yarkovsky measurement, combined with the 2021 radar observations that reduced the position uncertainty to a few kilometers, was sufficient to confirm that the 2029 trajectory would carry Apophis safely outside the 2068 keyhole. The force that Yarkovsky described in a pamphlet in 1900, the force that was forgotten for decades, the force that was not even measurable on Apophis until 2020 when the best available telescopes finally achieved the required precision, turned out to be one of the decisive factors in whether Apophis would or would not pass through a region of space approximately 2 meters wide during a close approach in 2029. The Yarkovsky effect will not stop acting on Apophis in 2029, it will continue after the flyby. But after the 2029 encounter changes the asteroid's spin state, the Yarkovsky effect operating on the post-flyby Apophis will be different from the one measured before 2029. The spin axis will have shifted, the rotation period will have changed, the thermal emission pattern will be different. The 170 meters per year orbital drift that characterizes the current Apophis will become a different number, pointing in a different direction after the flyby. Scientists will not know the new value until they can measure it, and measuring it requires the kind of long baseline observation campaign that OSIRIS-APEX will be able to conduct over the 18 months it spends at the asteroid after 2029. This is one of the specific reasons why the OSIRIS-APEX mission is designed for an extended stay rather than a quick flyby. The Yarkovsky effect is not something you can measure from a single observation, or even from observations spread over a few weeks. You need to track the asteroid's position over months, comparing where it is with where the gravitational model predicts it should be, and derive the residual acceleration from the systematic discrepancy. 18 months of OSIRIS-APEX observation will produce a Yarkovsky measurement for the post-flyby Apophis that will anchor the orbital calculations for the subsequent decades. There is something philosophically dense about what the Yarkovsky effect reveals when you trace it far enough. A tiny force, so small it cannot be directly observed, derived from the infrared emission of thermal energy absorbed from a star 150 million kilometers away, has been operating on this asteroid for 4.6 billion years, and for the past 20 years has been the marginal factor determining whether it passes through a keyhole measured in meters. The accumulated effect of sunlight on a rotating rock operating across geological timescales produces a displacement in 2029 that is either inside or outside a safety margin smaller than the width of a typical room. The universe operates at precision that human engineering is only beginning to approach. The GPS satellites that circle the Earth at 20,200 kilometers altitude are precise enough to detect the relativistic slowing of time at their orbital distance, a consequence of general relativity that must be corrected for in their clock systems or their position data would drift by kilometers per day. The orbital calculations for Apophis are precise enough to identify a 2-meter wide keyhole as either containing or not containing the asteroid's predicted path. These are achievements of measurement that would have seemed like science fiction to the physicists who first worked out the relevant equations, and underneath all of this precision, pushing the rock slowly toward or away from the keyhole by 170 meters per year, is the warmth of the sun absorbed by one side of a rotating stone and radiated back into space by the cooling opposite side. Physics working at scales so different from each other that the connection between them is not intuitive. The sun, a rock, the warmth of one surface facing away from the light, a 2-meter target at 32,000 kilometers, all of it connected by equations that Yarkovsky sketched out in a pamphlet that almost no one read before he died. What other forces too small to measure directly are right now determining the future of objects we have not yet discovered? There is a period of time between where we are now and April 13th, 2029 that does not receive much attention in coverage of the Apophis story. The years between the last major tracking update and the arrival itself, the interval, it is not a dramatic period. No spacecraft are landing on anything. No impact. After delivering the Bennu sample capsule to Earth in September 2023, the spacecraft used what remained of its fuel and its operational systems to set itself on a course that would take it, over the years between then and April 2029, through a series of orbital maneuvers, solar encounters, and Earth gravity assists that will position it correctly to meet Apophis at the moment of the flyby. The team managing the mission, now led by principal investigator Danny Mendoza della Giustina at the University of Arizona, monitors the spacecraft continuously, checking instrument health, managing the thermal environment as the spacecraft makes close passes to the Sun on its transit trajectory, and preparing the observation sequences that will begin executing in April 2029. In January 2024, Osiris Apex passed within 25 million miles closer to the Sun than it was designed to operate, a trajectory necessity imposed by the orbital mechanics of reaching Apophis. The spacecraft survived this solar encounter in better condition than pre-encounter analysis had predicted. Some instruments actually performed better than expected after exposure to the elevated temperatures. The spacecraft is functional, its instruments are healthy, and it is on course. The ESA-Ramses mission is in a different phase of the interval. The decision to commit fully to the mission was made at ESA's Ministerial Council meeting in November 2025. The mission requires a launch in April 2028 to make the February 2029 arrival at Apophis before the closest approach. This means Ramses is currently in the intensive development phase, with spacecraft design being finalized, instruments being built and tested, launch preparations being coordinated with the launch vehicle provider. The window to get Ramses to Apophis before the flyby is narrow, and the development timeline is correspondingly tight. The science returned from having a spacecraft at Apophis before the flyby, capable of establishing the baseline measurements that make the after-flyby data meaningful, justifies the pressure of the schedule. Ground-based observatories around the world are planning their own Apophis observation campaigns for 2027, when the asteroid reappears in the observable sky after the solar conjunction gap, and for 2028 and early 2029 as the approach date draws closer. The International Asteroid Warning Network, which coordinates near-Earth object observations across multiple countries and institutions, has Apophis on its agenda for sustained multi-facility observation in the years leading up to the flyby. The 2027 reappearance is significant for the reason discussed in the context of Paul Vigert's work on the possibility of undetected small body impacts. When Apophis comes back into view in 2027, the planetary tracking community will take the first new position measurements since the 2021 radar campaign and compare them with the trajectory predicted from those 2021 data. If the 2027 position is consistent with the prediction, the safety assessment is reinforced and the flyby proceeds exactly as planned. If there is a discrepancy, the source of the discrepancy will need to be investigated, and the orbital solution will need to be updated accordingly. The probability of any concerning discrepancy is very low, but the 2027 observations are not routine. They are the first opportunity to confirm with new data that the asteroid is where it should be. What happens in this interval, the patient ordinary work of monitoring and preparation and instrument testing and trajectory planning, is the part of planetary defense that never makes the news. The dramatic moments are the discoveries, the probability spikes, the confirming observations that clear an object from the risk table or deepen the concern. The interval between the dramatic moments is where the actual work of maintaining planetary defense capability gets done. The surveys continue running, the follow-up observations continue being collected, the orbital solutions continue being updated as new data comes in. The spacecraft systems continue being monitored and maintained. The mission operations teams continue running simulations of the April 2029 observation sequences, refining the protocols, preparing for contingencies. This work is invisible from the outside in the way that all sustained institutional effort is invisible until it produces a visible result. The result in this case will be the most comprehensively observed asteroid flyby in history, documented by 3 spacecraft and every major ground-based observatory on Earth. That result will appear, to anyone watching from the outside, to arrive fully formed at the moment of the flyby. What will be invisible is the years of preparation that made the comprehensive documentation possible. The interval is also the period during which the public understanding of what is coming is being built and rebuilt and built again through science communication, educational programs, news coverage, and the steady accumulation of detailed anticipatory explanations that will allow the 2 billion potential witnesses to understand what they are looking at when April 13th, 2029 arrives. This work of explanation is not separate from the planetary defense mission. It is part of it, because the political and institutional support required to sustain a planetary defense capability across the decades needed to develop and refine it requires a public that understands why the work matters. Every article written about Apophis before the flyby, every documentary, every classroom lesson, every casual conversation in which someone explains to someone else what an asteroid is and why this one is worth looking up for, is part of the infrastructure of public understanding that will determine whether the 2029 event produces the increase in planetary defense support that the scientific community hopes it will. The science is one piece of what happens in the interval. The communication of that science to the billions of people who will watch the asteroid go by is another piece, equally important and equally sustained. The god of chaos is approaching on a schedule that was calculated 25 years ago. Everything that needs to happen before it arrives is happening now, in the interval, in the ordinary invisible work of people doing their jobs. They do not need the event to be dramatic to understand why the work matters. They already know. The 2 billion witnesses will learn this in April 2029 when they look up and see something moving that the scientists have been tracking for their entire adult lives. That is what the interval produces, not silence, readiness. There is a version of this story in which the April 13th, 2029 flyby of Apophis is simply an event. A close approach, notable for its proximity and its visibility, interesting for the data it will generate, but ultimately a single point on a timeline that continues before and after it in ways that make the event itself less remarkable than the surrounding narrative suggests. This version of the story is technically defensible. The physics does not pause for reflection. The solar system does not arrange its events to carry meaning. Apophis will pass through the satellite zone, the data will be collected, the orbital parameters will be updated, and the asteroid will continue on its way. But there is another version. The version that emerges when you think carefully about what human civilization will look like on the other side of April 13th, 2029, and how it will be different from what it looked like before. And this version is, I think, the one that matters more in the long run than any single dataset that OSIRIS, APEX, or Ramses will ever return. Consider what will have changed in the years immediately before the flyby. The Vera C. Rubin Observatory will have been operating for several years, generating a flood of new asteroid discoveries and a correspondingly expanded catalogue of known near-Earth objects. The planetary defence community will have been processing this flood, conducting follow-up observations, refining orbits, clearing newly discovered objects from the risk table, or elevating their concern level based on what the follow-up data shows. The public will have been receiving regular updates about near-Earth object discoveries, not at the rate of the occasional alarming headline, but at the rate of a systematic, ongoing scientific process that is visibly working in real time. The Apophis flyby, in this context, will arrive as a culmination rather than a surprise. It will have been anticipated for years. It will have been explained and re-explained in educational contexts, in science communication, in the popular press, in school curricula. The 2 billion people who will be able to see it will have been told, in many cases, that it is coming, when it will be visible, what it will look like, and what it means. Some fraction of them will look up prepared. Some fraction will look up unprepared but curious. Some fraction will not look up at all because they do not know, or do not care, or live in circumstances where looking up at a moving star is not a priority. But the fraction who do look, and who see the point of light moving across the sky, will have experienced something that has never been available to any human generation before. They will have seen, directly, a large asteroid passing close to Earth, predicted years in advance, observed by 3 spacecraft at close range, tracked by every major ground-based observatory on the planet, visible with the naked eye from 3 continents. The completeness of the scientific coverage of this event, the depth of the preparation, the precision of the prediction, will be apparent to anyone who follows the story at any level. And the story is that the system worked. From discovery to assessment to tracking to prediction to confirmation to observation, every component of the planetary defence infrastructure performed its function. The political and institutional consequences of a system that visibly works, demonstrated at this scale, in this way, to this many people, are genuinely hard to predict. But the direction of the effect seems clear enough. Planetary defence programs have historically been funded at levels that reflect a substantial gap between the scientific assessment of the risk and the public's felt urgency about it. The risk is real. It is well characterised at the larger size scales. It is known to be significant but manageable with adequate advance warning and the right technology investment. But the felt urgency, the visceral sense that the problem is pressing rather than theoretical, has always been harder to sustain in competition with other priorities. Asteroids have not struck a populated region in recorded history. The closest events, the Tunguska explosion in 1908 and the Chelyabinsk airburst in 2013, did not kill anyone directly, though Tunguska flattened thousands of square kilometers and Chelyabinsk injured more than 1,500 people. The planetary defense case has always been made with reference to probability distributions and geological records and theoretical impact models, not lived experience. After April 13, 2029, 2 billion people will have lived experience. It will not be the experience of being struck, but it will be the experience of having watched the closest approach of a large asteroid to Earth that any human generation has ever witnessed, and having seen the scientific infrastructure predict it accurately and study it comprehensively. The narrative that emerges from this, the narrative of a system that saw it coming, that tracked it for 25 years, that sent 3 spacecraft to observe it, that correctly calculated where it would pass and by how much it would miss, is a narrative of scientific competence at civilizational scale. Civilizational scale demonstrated competence has historically been the most effective argument for continued investment in a scientific capability. Not the abstract case that the investment is prudent, the concrete demonstration that the investment produced a result that mattered. The Apophis flyby will produce that demonstration in a way that no previous planetary defense achievement has matched, because no previous planetary defense achievement was directly visible to 2 billion people over the course of an evening. The DART impact on Dimorphos was an important engineering achievement, but it required a telescope to see and knowledge of what you were looking for to appreciate. Apophis will require neither. It will be in the sky, moving, visible to the unassisted human eye for hours. There is also a change that the flyby will produce in the scientific community itself, independent of its public and political effects. The Apophis encounter is the first time in the history of asteroid science that a significant near-Earth object will be studied with dedicated spacecraft before, during, and after a major gravitational perturbation. The data returned from Ramses and OSIRIS-APEX will anchor an entirely new generation of models for rubble pile asteroid dynamics, tidal deformation, surface modification, and post-encounter orbital evolution. These models will be applied not only to future Apophis predictions but to every other rubble pile asteroid in the catalogue. The 40% of the city-killer size range that is currently catalogued will be assessed with calibration data that did not exist before 2029. The 60% that remains to be discovered will be characterized, when found, using techniques informed by the Apophis observations. The next potentially hazardous asteroid that generates an elevated impact probability will be assessed by a scientific community that has observed a real close encounter at close range, not just modelled one. Apophis transitions from a teen class to Apollo class as a result of the 2029 flyby. Its orbital period changes permanently from approximately 0.9 years to approximately 1.2 years. It moves from a group of asteroids whose orbits are smaller than Earth's to a group whose orbits are larger. The asteroid will continue to cross Earth's orbital path periodically, as Apollo-class asteroids do, but on a different schedule and from a different geometry than before. The long-term future of Apophis's orbit, and whether it generates future keyhole scenarios on the multi-century timescale, will be calculable from the post-flyby observations with a precision that current models cannot achieve. This permanent reclassification of Apophis is a physical consequence of the encounter, not a procedural one. Earth's gravity is literally reshaping the object's trajectory through the solar system. The planet that Apophis threatened in 2004, whose gravity it will pass within in 2029, will have permanently redirected it onto a different path. The god of chaos, named for the serpent who sought to consume the sun, will be changed by its encounter with the third planet from the sun. Earth will have left its gravitational fingerprint on Apophis's orbit, and Apophis will carry that fingerprint for the remainder of the solar system's life. There is something in that image that deserves a moment of quiet reflection. Not because it is threatening or frightening, because it is extraordinary. A planet and an asteroid, both formed from the same cloud of gas and dust 4.6 billion years ago, following separate paths for 4.6 billion years, converging in 2029 close enough that the planet's gravity changes the asteroid's future forever, and then separating again, the asteroid carrying the mark of the encounter in its orbit and its spin and its surface for billions of years to come. The universe arranges these convergences without intention or design. They are the output of gravity and initial conditions playing forward through time according to rules that have no awareness of the significance we assign to their products. But the significance is real, even if the arranger is not aware of it. And the significance of this particular convergence, this particular outcome, is that for the first time in the history of the system, the species on the planet that the asteroid passed will have watched it happen, measured it completely and understood it. That is what 2029 changes about everything that comes after it. The question of whether humanity can protect itself from the natural hazards of the solar system has always been open. After 2029, the community of people who have thought carefully about that question will have new data, new models, new institutional experience, and 2 billion new witnesses to the argument for why the question matters. What does it mean to live in the first generation that watched an asteroid pass through its satellites and understood exactly why? Apophis will be gone from the naked eye sky within hours of its closest approach. The point of light that 2 billion people watched will fade below the threshold of unaided human vision, and the asteroid will recede into the dark, becoming again a number in a database, a coordinate on an orbital map, an object of continuing scientific interest to the missions following close behind it, and the ground-based instruments tracking its post-flyby parameters. By June 2029, OSIRIS-APEX will have caught up to it. The spacecraft will begin its 18-month investigation, mapping the surface, measuring the spin, characterizing the composition, documenting what Earth's gravity did to the surface in the hours of closest approach. The boulder that shifted will be recorded. The fresh material exposed by the disturbance will be analysed. The new rotation period will be measured. The Yarkovsky effect will be remeasured for the post-flyby asteroid on the post-flyby orbit. All of this data will be transmitted to Earth by a spacecraft travelling in the dark, a few hundred kilometers from a slowly tumbling rock, both of them moving through the inner solar system at tens of thousands of miles per hour, and the signal arriving at receiving stations that were built by people who will read the data on screens in offices and write papers about it for decades. This is how science works at the scale of the solar system, not in moments of drama, though April 13th, 2029 will be genuinely dramatic, but in the long, patient accumulation of measurements over years and decades by instruments and institutions built by people who understood that some problems require sustained attention rather than episodic effort. The story of Apophis is ultimately a story about what happens when a civilization builds the capability to see what is coming before it arrives. The capability was not built in response to Apophis. It was built in response to the recognition, accumulated over decades of careful work by people who studied the geological record and ran the probability calculations and understood what the numbers implied, that the solar system is not an empty backdrop to the drama of life on Earth. It is an active environment. It produces events. Some of those events, on geological timescales, are catastrophic for whatever is on the surface of the planet when they arrive. The dinosaurs were not warned. Whatever species preceded them and were ended by earlier impact events in the geological record were not warned either. Every mass extinction event attributable to an impact in the history of life on Earth occurred without any species having the awareness to see it coming or the technology to do anything about it if it had. We are the first species in 4.6 billion years of this planet's history that has both. Not perfectly. Not with the completeness that would make the planetary defense problem fully solved. The catalogues are incomplete. The survey systems have blind spots. The deflection technologies are real, but untested at full scale. The international coordination mechanisms are functional, but not seamlessly integrated. There is more work to do, a great deal more, before the planetary defense enterprise can be described as fully adequate to the hazard it is designed to address. But the trajectory is toward adequacy, not away from it. The survey completeness is improving year over year as new facilities come online and processing techniques improve. The deflection technology has been demonstrated at small scale and will be refined and tested further. The international coordination mechanisms are strengthening with every shared observation campaign and every jointly conducted mission. The scientific community's understanding of asteroid properties and behavior is deepening with every new data returned from a mission like OSIRIS-APEX or Ramses. And in April 2029, for a few hours on a Friday evening, 2 billion people will be able to look up and see the asteroid that started the modern era of planetary defense and watch it pass by, close enough to be real, far enough to be safe, and carrying in its trajectory the accumulated work of 25 years of careful measurement. The planet it passes will be different from the one it would have approached without the warning. Not different in any physical sense. The presence of the planetary defense infrastructure did not change the trajectory of Apophis. The asteroid is going to pass where it was always going to pass, on a path determined by forces operating across billions of years before anyone was watching. What is different is the capacity to know it is coming, the capacity to understand what it is and what it would do, the capacity, in principle and increasingly in practice, to intervene if the calculation ever comes out differently. That capacity is new. It is 1 generation old. It is the first generation in the history of this species that has looked at the sky and understood that the rocks in it are real, that some of them are coming toward us, and that this is a problem we are capable of solving if we commit the resources and the attention it requires. Apophis will be visible to the naked eye from 3 continents on one April evening in 2029. Then it will be gone. The god of chaos will depart the satellite zone, altered by the encounter, and continue on its new orbit through the inner solar system, carrying Earth's gravitational fingerprint in its trajectory for billions of years to come. What it leaves behind on Earth is not a crater or a memory of destruction. It leaves behind the knowledge that the sky has been watched, that the watching worked, that the tracking system produced the right answer, and that the species on the planet below had the tools and the will to understand what was passing overhead. The universe arranged this encounter without awareness. It did not know what it was offering, but the species that watched it knew exactly what it was watching, and will spend the next century making sure the watching never stops. That is the story of Apophis, not the god of chaos defeating the sun, not the eternal serpent swallowing the light, a rock, a planet, a species with telescopes and spacecraft and equations, and enough time to understand that the neighbourhood they live in is not as empty as the darkness makes it look. We are not the first species to have been in the path of something coming from the dark. We are the first species to have known it was coming. We are the first species to have named it, measured it, calculated its path, dispatched machines to ride alongside it, and stood under the open sky waiting for it to appear, knowing exactly when and where and how bright it would be. That is not a small thing. It may, from some future vantage point, look like the moment a species decided to stop being the passive recipient of what the universe delivered and to become something more deliberate, something that watches, something that prepares. Apophis will be gone by morning, the watching will continue, sleep well, the sky is being watched. Consider the full arc of what this moment represents when you stand far enough back to see it whole. In 2004, 3 astronomers at a telescope in Arizona found a point of light moving across a series of images and logged it in a catalogue. They did not know what they had found. They knew only that something was there that had not been noticed before, following an orbit through the inner solar system that brought it periodically into range of the instruments that humanity had built to watch the sky. The detection was routine in process and extraordinary in consequence. The process was systematic sky survey, repeated observation, astrometric measurement, orbital calculation. The consequence was the discovery of the most alarming near-Earth object in the history of the discipline and the beginning of 25 years of work that will culminate in April 2029 with the most comprehensively observed asteroid flyby in history. The 3 astronomers could not have known, on the night of June 19, 2004, that what they were logging would occupy the attention of planetary scientists for the next quarter century. They could not have known that the point of light they flagged would generate probability estimates that terrified people who had spent careers thinking about exactly this kind of event. They could not have known that it would be named for the Egyptian god of chaos, or that it would arrive on a Friday the 13th, or that 3 spacecraft from 2 space agencies would be dispatched to study it, or that 2 billion people would be positioned to see it with their naked eyes on the evening of its closest approach. They found it because the survey system was designed to find things like it, and they ran the system with the care and consistency that systematic science requires. They did not do this because they knew Apophis was there. They did it because they knew that objects like Apophis were out there, distributed through the inner solar system in numbers that the catalogue had not yet fully enumerated, and that finding them required exactly this kind of sustained, patient, methodical looking. The survey found Apophis. The tracking system characterized its orbit. The radar observations refined the trajectory. The modelling community computed the impact probabilities, and then the keyhole scenarios, and then the margins of safety. The mission designers developed Osiris, Apex, and Ramses, and positioned them for the 2029 encounter. The science communicators explained the story to the public. The public, in the nations with the best science communication infrastructure, followed the story and understood, at least in broad outline, what it meant. All of these things happened because people made choices to build systems capable of doing them. The survey telescopes were funded, the orbital calculation software was developed, the radar observatories were maintained, the planetary defense coordination bodies were established, the spacecraft were designed and built and launched, the science communication programs were created and sustained. None of this was inevitable. All of it was chosen. The choice that underlies all the others is the choice to pay attention to the sky. Not casually, in the way that humans have always looked up at the stars and wondered, but systematically, with instruments designed for detection and measurement, with institutions designed for sustained vigilance, with resources allocated across decades on the premise that the neighbourhood we live in deserves our full attention, and that the attention will eventually matter. In April 2029, the attention will visibly and demonstrably matter, in a way that 2 billion people will be able to see. An asteroid that was once assigned a 2.7% probability of striking Earth will pass through the satellite zone at 26,500 miles per hour, visible to the naked eye, tracked by 3 spacecraft, calculated to the nearest kilometre, understood in detail that would have been impossible to any previous generation of human beings. This is what it looks like when a civilization decides to see what is coming. It looks like 3 astronomers at a telescope in Arizona on a June night in 2004, running a systematic survey, logging what they find following the process. It looks like orbital mechanics calculations and radar campaigns, and probability assessments and mission proposals and instrument designs and launch schedules and the long patient work of institutions sustained across decades. It looks like a point of light moving across the sky on an April evening, visible to 2 billion people, exactly where it was predicted to be, exactly as bright as the calculations said it would be, on a trajectory that the measurements confirmed years in advance would carry it safely past. It looks like nothing dramatic at all from a distance. Only from close range does the extraordinary nature of what it represents become apparent. The species on the planet below the asteroid's path built the system that found it, tracked it, understood it, and watched it go by. That is not a small thing. That is, in the full history of life on this planet, an entirely new thing. The sky is being watched. The watching worked. And on a Friday evening in April 2029, 2 billion people will look up and see the evidence of that with their own eyes. What you do with that knowledge is up to you.